Okay, so this is 4.44 E equal to 4.44 F into the flux, and then you have the N. Can anyone tell me what this equation is? You must have encountered this equation before as well. Not. तो बताएगा मुझे. E is equal to 4.44 F flux phi N. इक्वेशन कहाँ से आई, क्या बता रही है, किस तरह से? बेटा आप बेटा आपको कह रहा हूँ जी. anyone on this 4.44 F phi N. This E is actually the same thing, or the applied voltage. You don't confuse this one. Same thing actually. E is the induced EMF if I'm talking about the Faraday's law of electromagnetic induction. जी, तो बताएगा ये कैसे है, क्या है, कहाँ से आया है ये and all that. जी, anyone wrong or right, please just give me a hint on this one. जी, no one? क्या है इसमें? ये फ्लक्स फाई क्या चीज़ है, एन क्या है यहाँ पे? नंबर ऑफ टर्न्स. 4.44 from where this is here? Any idea on this one? अच्छा, चलो, I will just go on this. Whenever you are talking about a transformer, you are always using the Faraday's law of electromagnetic induction, and we know that is equal to N d phi by dt, which means N is the number of turns and d phi by dt is the rate of change of flux which is happening inside that transformer. Now, when I have a transformer into consideration, certainly this means that you are applying a sinusoidal waveform. Now, technically speaking, majorly whenever a transformer is applied a sinusoidal waveform, the waveform of the flux is not sinusoidal. Why it is not sinusoidal? Because if we go into a little bit depth of the BH curve, the BH curve, we all know it goes up till linear up to some region, and then afterwards it saturates. And then afterwards it saturates. If it's supposing a transformer is working at this point, so and you take the H, what is H equal to? For those who are still lagging behind, H is equal to Ni divided by Lc by Ampere's law. Okay? This is from the first chapter, Chapman, the magnetic circuit chapter. So when this N is the number of turns, Lc is the mean length over there, I. So when you plot this I on the time graph, you get something, a waveform like this. You will get something, third harmonic component induced over there, and you will get something like this, a huge increase at that. Why this is a huge increase over there? Because after this point, which is actually the linear point over there is a huge increase in current for a very small increase in D. So the waveform of the current being taken by the transformer is not sinusoidal. So now I am assuming over here that I am not going in the saturation region, I am just in this region which is actually the linear region over here, which means that D and H are completely linear over there. The mu r which I am considering over there, that is completely constant, and this is linear. So based on this one, the current waveform or the flux waveform over here, this is going to be sinusoidal, and this phi m is the maximum flux that is going to be achieved. Okay? So I am taking this one because normally whenever a transformer is working, the manufacturer is always going to try to use something this color waveform. Why? Because using this waveform means that he has actually chosen a large value of V, which means the material is going in saturation. He has chosen large V, so less area is required. So he is actually saving some cost of the material and giving you a substandard thing. But again, being idealistic, I am assuming that we are just in the linear region. So when we are in the linear region, the current taken up is sinusoidal. The flux waveform that is induced inside that is actually produced inside the core is also sinusoidal. Now, when you have a sinusoidal flux waveform, this is the total time over here on the x-axis. From this point up till this point, this is the total time t for the given frequency, whatever that voltage applied was. So based on this one, now here if I want to find out that what is, if my flux has gone from this zero value to flux phi m, how much time it has taken from here to here. since this is quarter of the whole cycle, this time would be equal to T by 4. Okay? From 0 to 90 degrees. So when I'm talking about rate of change of flux d phi by dt, what is d phi here, which has taken place from this point to this point? The change in flux is phi m. Okay? So here in the numerator I have phi m, and in the denominator I have T by 4. So here I have T by 4. Now what is T? This is a time period which can also be written as 1 over f. That is frequency. So I can write this one as phi m divided by 1 over 4f, or just rearranging it again, this is d phi by dt equal to 4f phi m. Now this is telling you the rate of change of flux for a transformer which is going from 0 to phi m. Now if you know a sinusoidal waveform, if I just zoom in over here, in the very start over here, the rate of change of flux is very large. Then afterwards, in the next region, it is a little smaller. And then when it reaches the maximum point, the rate of change of flux is almost 0. So what we are doing over here, this d phi by dt which we have calculated just now is not the actual rate of change of flux. This is actually the average rate of change of flux over there. Because we took the initial value, we took the final value, and we divided it by the total time. So this is the average rate of change of flux. Now, since this is the Faraday's law of electromagnetic induction, we know what is E. E is equal to N d phi by dt. What is N? N is the number of turns. And if I have N number of turns in my transformer, so this will be equal to N 4 f phi m. But the problem is this, that since this term was average, I have average value of the voltage. Okay? Because d phi by dt which I calculated, this was average value. Now whenever you have an average value of voltage and you have a sine wave, this is actually now a hint of from your previous course, what is the relationship between average value and RMS value? G. What is the relationship between an average value and an RMS value for sine wave? Arun H. Rashid, Power Electronics course, you have done this. पिछले सेमेस्टर ही है ना, इसमें ही पढ़ा है ना अभी पावर इलेक्ट्रॉनिक्स जी. दोबारा. There is a factor in between. What is that factor called? There is a factor. याद आया? Form factor. RMS value divided by average value, there was a form factor. And for sine wave, this form factor was equal to 1.11 for RMS divided by the average value. Now here you know the average value. Average value we already know of E average. This is equal to N4FIM. So this means if I am interested in ERMS, this is going to be equal to 4.44, because 4 into 1.11 is equal to 4.44 F flux phi into N. This is the same equation which I told you in the very start. Now, this equation is not just limited to a transformer. This is very important. This equation is for any electromechanical device, even a fan, any induction motor, any single phase machine. This is applicable over there. Why it is applicable? Because all these machines are working on an electromechanical principle in which you are transferring one form of energy into the magnetic field and using that magnetic field and electrical energy to produce some motion. In case of a machine, that is actually a motor. Or if it's a transformer, you are converting it back into electrical energy with a different step up or step down ratio. So this equation E is equal to 4.44 F phi N is actually the first building equation for any electromechanical device or any electromagnetic device. The word electromechanical normally is used for something in which you are having a mechanical structure that is actually moving or dynamically. In transformer you don't have anything moving. ठीक है? And the only reason, since I'm talking about this at present, one line statement over here, in transformer and induction machine there is only one difference. The equivalent circuits are exactly same. The only difference is this, that in a transformer the axis of the windings, they are parallel to each other. In induction machine, the axis of the windings, they are displaced by 120 degrees for a three-phase machine. I'm again repeating. In transformer, the axis of the windings, they are parallel to each other. So if this is limb A, this is for the first winding, phase A, phase B, phase C, three phases. They are all having the axis straight line. They are parallel to each other. But when you have an induction machine, it is circular. The A winding has an axis like this, B winding has an axis like this, C winding has an axis like this. So they are 120 degree spaced. अगर आप ट्रांसफार्मर के अंदर भी वाइंडिंग्स को एक्सिस के हिसाब से डिस्प्लेस कर दो, the transformer will start to rotate, and that's the same thing as like an induction machine. Okay, coming back to this one, since this is E is equal to 4.44 F phi n, E RMS, you can write this one as 4.44 F. Now instead of phi, this was phi m actually, because this was the maximum flux, you multiplied this one or replace it by BM into AC. What is BM? Maximum flux density on your BH curve. Here in this case, we assumed it that our BM was up till this point, because we were in the linear region. But now, since we want to use this equation for the practical also, we assume it can go up till here at this point. There will be some problems, there will be a little bit deviation from the ideal nature, but we assume it that all the manufacturers will not go much deeper into saturation line. They will remain close. This point, since you are doing with the protection course also, you will have an idea that this is called as the knee point. Okay? The point at which the saturation starts at a BH curve, this is called as the knee point. So this knee point is actually the point where the manufacturer should decide. So you have this value and multiplied by n. Now a question here. In machines course you were told that a transformer can be a step up or step down. आपको कहा जाता है जी कि एक 1:2 ट्रांसफार्मर बनाना है, which means you are stepping up the voltage 2 times. So can a transformer can be made of कि जी मैं randomly एक select करूँ on the primary side or the low voltage side मैं 100 turns कर देता हूँ और secondary side पे मैं 200 turns कर देता हूँ. Will that transformer work? No. You have to pass that 100 turns through this equation, which means you have to have 100 put at this RMS value. 4.44 is a constant, frequency F is 50 Hertz, BM is your material dependent that you are having at 1.5 Tesla, 1.7 Tesla or whatever. Area of the core is the variable quantity over there. आपने एरिया ज़्यादा रखा, आपका कोर लॉसेस ज़्यादा भी हो सकते हैं. एरिया कम रखा, BM बढ़ जाएगा, because फ्लक्स उतना ही चाहिए आपको. So N is going to be the output equation from here. इस इक्वेशन के अंदर BM, AC, F और ERMS डालने के बाद आपके पास जो एंड आता है, that is the minimum number of turns you require for your transformer. And if after putting in this equation, it comes out to be okay 130 turns. Now in that 130 turns, if you put on the primary side and on the secondary side you put 260 turns, now this is going to work. But practically on the secondary side आप इसको थोड़ा सा ज़्यादा रखोगे, because your transformer is being made, you are going to have losses, you are going to have voltage drops. So आप 260 की बजाय maybe 270, 280, a little bit higher, so that even at load that transformer is still giving you the double the voltage. Okay? So this equation is the first building block for any machine, either a transformer or even a machine. Supposedly an induction machine, आपने number of turns निकालने हैं stator winding के अंदर. This equation is going to be the same basic form. You know BM, you know AC, you know your n number of turns, you can find out from this equation. One thing very important, in your machines course you were told that V by F ratio is a very important factor. This factor is very important for transformer also. Why important? Because your voltage is the rated value at which your transformer can work. अगर आपके पास एक ट्रांसफार्मर है, I have got this transformer over here, this is a shell type transformer over here, ठीक है? In this shell type transformer, it is winded over here based on 200 volts on this side and maybe 12 volts on this side. Now 200 volts आप इसको दे सकते हैं. If you try to give more than 200, the winding insulation will be damaged. By winding insulation, I mean that this is a shell type transformer. In the central core, you have all the winding. First of all, you will do the low voltage winding, and then on that one, you will do the high voltage winding. Now, on the high voltage winding, which is on the outer part, certainly here, if you give more than the rated voltage, the insulation will not withstand, and between the two turns, there will be a spark, which means the dielectric strength of that insulation cannot withstand that voltage. So if a transformer is designed for 200 volt or 220 or something voltage, it has to keep at that voltage. You can give less. आप less दे सकते हो, no issues. But if you are giving less voltage, this is very important, and you are going to keep your frequency same, no issues in the transformer overall. Why no issues? Because in a transformer equivalent circuit, if I draw the equivalent circuit again, let me draw it again over here. Without naming all of them, this is R0, this is JXM. Now, if you are applying a less voltage on the primary side, what will happen? Less voltage on the primary side, secondary is still open circuit. Okay? Less amount of current is going to flow in I0. Less amount of current means that less amount of flux in the core losses भी कम होंगे, लेकिन एक minimum level of voltage चाहिए आपको ताकि I0 इतना हो सके, so that you can have a voltage available on the secondary side by electromagnetic induction. So transformer के अंदर, if you are changing the voltage, changing the frequency is not that important. But when you are working on an induction machine, listen to this carefully, then in that case, your frequency has to be also changed. Reason, listen this, in an induction machine, the equivalent circuit is the very same, no change. The only change is this, the rotor is short circuited, the secondary side is variable because the rotor is rotating. जितना slow speed से rotate करेगा उतनी ज़्यादा voltage है. Plus you have a frequency parameter. उस frequency parameter से क्या चीज़ change हो रही है? The reactance here, the reactance here, the reactance here. Why? Because x is equal to 2 pi fl. अगर आप frequency change कर रहे हो तो x पैरामीटर चेंज हो रहे हैं और x पैरामीटर JXM के यहाँ पे हैं, they are also changing. So when you are reducing your voltage, you have to reduce your frequency also. अगर आप voltage reduce कर रहे हो तो frequency को भी reduce करना है, so that the same amount of I0 flows over there. अगर आपने frequency reduce नहीं की तो क्या होगा? I0 करंट कम होगा, मैग्नेटिक फील्ड कम प्रोड्यूस होगी इंडक्शन मोटर के अंदर. एंड ये I0 कौन सा फ्लक्स है? जो एयर गैप के अंदर होता है मशीन के अंदर. तो जब फ्लक्स कम होगा, मैग्नेटिक फील्ड कम होगी, द मोटर इज नॉट एबल टू प्रोड्यूस द सेम अमाउंट ऑफ टॉर्क. सो इफ यू वांट द सेम वैल्यू ऑफ टॉर्क, एट लीस्ट एट दैट वैल्यू, देन यू हैव टू हैव V/F रेशियो कांस्टेंट. हाँ, इंडक्शन मशीन के अंदर इफ यू आर इंक्रीजिंग V, दिस विल नॉट वर्क, मशीन डैमेज हो जाएगी, बिकॉज अगेन इंसुलेशन इज नॉट गोइंग टू वर्क ओवर देयर. फ्रीक्वेंसी आप बढ़ा सकते हैं, वोल्टेज नहीं बढ़ा सकते. फ्रीक्वेंसी बढ़ाने का हमें फायदा क्या था इंडक्शन मशीन में? स्पीड इंक्रीज हो रही थी, लेकिन वोल्टेज वही के वही रहेंगे, तो V/F रेशियो कम होगा, फ्लक्स कम होगा. जब फ्लक्स कम होगा तो टॉर्क कम हो जाएगा. लेकिन इंडस्ट्री के अंदर जब भी आपने इंडक्शन मशीन को इस्तेमाल करना है, आपको स्पीड ज़्यादा चाहिए, लेकिन उस स्पीड ज़्यादा के ऊपर टॉर्क कम चाहिए. सो एक 10 न्यूटन मीटर की मशीन 5 न्यूटन मीटर भी दे देती है तो योर वर्क इज डन. सो व्हेनेवर इन द इंडस्ट्री यू आर डिजाइनिंग और यू आर सेलेक्टिंग अ मशीन, आप हमेशा हायर वैल्यू पे वैल्यू सेलेक्ट करोगे, सो दैट यू कैन गिव अ हायर फ्रीक्वेंसी, रन दैट मशीन एट अ डिफरेंट स्पीड, एंड देन हैव लेस टॉर्क आउट ऑफ दैट मशीन. ठीक. Any questions जी? Any questions on this one? 4.44 F DM AC into N. Okay. Coming on to देखो एक सेकेंड, एरिया इज डिपेंडेंट अपॉन द वैल्यू ऑफ फ्लक्स इन द कोर, ठीक है। एरिया ऑफ द कोर सेम रहेगा, उसको कोई फर्क नहीं पड़ेगा। यस, द प्रॉब्लम क्या पड़ेगी, आपका एरिया ऑफ द कोर उतना ही है, लेकिन आपने क्योंकि वायर का साइज बड़ा करना है, तो दिस आउटर डायमेंशन विल इंक्रीज, क्योंकि उसके बीच में अब ज्यादा मोटी तार आने हैं। आपको बड़ा करना पड़ेगा फिर उसको, इसीलिए यू हैव टू फर्स्ट मेक इट ऑन अ पेपर एंड देन गो ऑन टुवर्ड्स इट। अब मिसाल के तौर पर एक छोटा सा क्वेश्चन है व्हिच आई आल्सो आस्क्ड इन द लास्ट क्लास आल्सो। आई हैव अ शेल टाइप ट्रांसफार्मर हियर, ठीक है। मैं इसको जरा मूव नहीं कर सकता बिकॉज ये आपकी केबल VGA की खराब है, मैंने इसको रखा हुआ है इस तरफ से। इफ यू सी ऑन दिस साइड, दिस इज वन सेट ऑफ वायर कमिंग आउट, वन पेयर, एंड इफ आई चलो, and on this side you can see there are different taps coming out. Now just by seeing this transformer, can you tell me which one is the low voltage side, which one is the high voltage side?
This one is low voltage.
How?
क्योंकि ये इसका कंडक्टर में होता है, इसमें करंट ज्यादा है।
This side has a larger thickness of the conductor, so this means certainly the current capacity is more. So when current capacity is more, this means that it is the low voltage conductor. This side is the capacitor, the cross sectional area is small, so here the voltage is high, ठीक है। हाँ, अगर it's a 1-to-1 ratio transformer then certainly I can't tell, but since this has a step up or step down, अब क्योंकि I know this transformer is a 220, from this side 220 to some 48 volt or 50 volt something over here, so I know what is the low voltage by N. And whenever you are designing a transformer, either a core type or a shell type, near the core you are always going to place the low voltage winding, because the core is electrically at neutral, it's grounded. So आपको नहीं चाहिए कि your core should have some current flowing through it. There will be some electrostatic current flowing over there. To avoid that electrostatic current and to keep that transformer insulation small, you will first of all place the low voltage winding, then some insulation, then maybe an oil duct, because if it is going to be immersed in oil, and then the last is the high voltage winding. Okay, now coming on to the very important thing. The first thing is single phase core type transformer. Now a single phase core type, whenever I am now going to make this a single phase core type, and I am going to use this green color for the low voltage winding. Now if you see what I am doing over here, I have made a two-dimensional picture and the transformer is cut like this. You are seeing this transformer, I have cut this transformer like this. In the previous class I showed you that it was cut like this and you are seeing from the top. Now I have cut this transformer, this is a shell type, वो भी मैं बनाऊंगा भी आपके सामने. This is cut like this. So you are seeing the half of the winding in front. So this is the low voltage winding on this limb, low voltage winding on this limb. अब लास्ट लेक्चर में मैंने आपको बताया था कि लो वोल्टेज वाइंडिंग एक लिम्ब पे करेंगे, हाई वोल्टेज वाइंडिंग एक लिम्ब पे करेंगे, बट यू कैन बाइफरकेट इट ऑन बोथ लिम्ब्स सो दैट द magnetic coupling between the windings is better. So here I have the low voltage winding and then there is a small duct. This is the high voltage and then this is the high voltage winding. So मैंने क्या किया है, I had n number of turns or n1 number of turns on the low voltage, half of the turns are here, half of the turns are low voltage are here. I can connect them electrically afterwards with the wires. So what I am doing over here, in this one, in this transformer, to increase the flux linkage, half of the windings of low voltage are here, half of there, same for the high voltage winding. Now before I proceed on further, some variables which I will be using a lot over here in this total derivations over here. whenever I'm using the word low voltage winding, okay, primary and secondary words is course may we will not be using. We always be using the low voltage and high voltage term. So when I'm talking about low voltage winding, then I will be using V1 and I1 as the attributes, the voltage and current rating I'm talking about, and I will be using A1, which is actually the cross-sectional area of the low voltage conductor, by which I mean the size of this conductor, cross-sectional area, and certainly the more common unit is this, that I will be using millimeter square. One thing very important in this course, have a habit in every step, please write down the units, or unit conversions बहुत important है. If you are working in millimeter square, keep it in millimeter square. If the question is somehow given in centimeter or centimeter square, first of all, first thing, whenever the question comes, convert it into your units or the asked units. This is very important. Okay, A1 is the cross-sectional area of the conductor, and delta 1 is the current density of the low voltage winding. Current density, what I mean by that? Current density means that how much ampere per millimeter square are going to be flowing inside the winding. Now, why this is important? This is important. अगर ये ट्रांसफार्मर इसी तरह का है जिस तरह का मेरे सामने इस वक्त है, it has no cooling mechanism. ये एयर में पड़ा है, मैं यहाँ पे 220 दूंगा, यहाँ से मैं कुछ 1248 वोल्ट लूंगा, मैं इस पर लोड बढ़ाता जाऊँ, will certainly heat up, a time will come, the winding will heat up. लेकिन अगर इसी ट्रांसफार्मर को मैं ऑयल के अंदर रख दूं, तो मे बी इसी वायर के अंदर से मैं ज्यादा करंट गुजार सकता हूँ, और अगर उसी ऑयल को मैं पंप के थ्रू फ्लो करवाना शुरू कर दूं, एंड देयर इज सम एयर ब्लास्ट आल्सो, देन आई कैन हैव मोर करंट. सो करंट डेंसिटी इंक्रीजेस इफ यू आर हैविंग सम फोर्स कूलिंग ऑप्शन available over there. So this delta 1 is very important. And similarly, just like this low voltage winding, for high voltage winding, the factors are again V2, I2, no need to tell about it, the voltage and the current, and then I have A2 as the cross-sectional area. This is the cross-sectional area of the high voltage conductor. And then I have the delta 2, which is the current density of the high voltage winding. Here, one thing very important. Whenever you are having the current density of delta 1 and delta 2, normally if your transformer is small and it is just air cooled, just like this transformer, then you will keep delta 1 and delta 2 same. But if in a case where your low voltage winding is done first, then there is an oil duct जिसमें से आपका oil flow कर सकता है, and then there is a high voltage winding, then the inner winding can have lower, the outer winding can have higher current density because it can dissipate more heat because it's on the outside. But here in this case, in this discussion today, I am keeping delta 1 equal to delta 2. Okay? Normally they will be kept same, but if it's a very big huge transformer, then there can be a 10 to 20% difference in them. Just because the outside winding is the other winding or the high voltage winding, so it can withstand a lot of heat over there, or it can dissipate that lot of heat over there. Now, when I'm talking about a single phase core type transformer, I know the value of S, apparent power of that transformer which I want to design, and I can write it as V1 I1 over there, that will be in VA terms. Now one thing very important in this design course or in transformer industry, we are always interested in the kVA rating, because distribution transformers, they are always in kVA. आप हमेशा वहाँ पे 400, 1000 VA नहीं लिखोगे, आप kVA rating लिखोगे. So the word normally used for S or the units are kVA. Now I have V1 I1 into 10 to the power minus 3 kVA. Now instead of this V1, I can write the same equation we have just proved just now. This is F phi m into N1 I1 into 10 raised to power minus 3 kVA. Okay? Instead of V, I just written 4.44 F phi, and instead of phi m, you can write BA as well. It's totally up to you. वो हम आगे जाके पूरा कर देंगे. Now, in this equation, there are many unknowns. You still don't know. First of all, S is known by you because आप एक ट्रांसफार्मर डिजाइन करना है. S आपको पता होगा कितने VA का ट्रांसफार्मर आपने डिजाइन करना है. फ्रीक्वेंसी भी पता होगी जिस पे आपने उसको वर्क करना है. You don't know the value of phi m. You don't know the value of N1. Yes, you know the value of I1 because you know the value of voltage. Now there are many unknowns in this equation, so we need some replacements over there. Now for this purpose, the first thing which we are going to do here, I am going to introduce a factor which is called as window space factor, and this is called as KW. And what is KW equal to? This is equal to actual copper area in window divided by window area. Now what I mean by this, if I go back on my diagram of the single phase co-type, if you see over here, I have used a lot amount of spacing over here, this spacing, and certainly this spacing. Now why this is spacing over there? This spacing is used for the oil duct. This spacing is used for the insulation. If I am designing a transformer which is very high voltage, that is supposedly 11 kV slash 400 volt, which means 11 kV is the high voltage winding, high voltage value, and 400 volt is the three phase low voltage value. So I will require more insulation between the low voltage and the high voltage winding. And if I am designing a transformer supposedly just 400 volt slash 400, both are the same value, so I don't require that much insulation. So this KW factor is actually going to be giving you a value of this shaded region. This shaded region over here is called as the area of the window AW. This shaded region inside this single phase core type is called as AW. Now inside this AW, how much copper is used divided it by the AW area, this is called as the window space factor. Now what is window space factor? If a transformer is higher voltage value transformer, window space factor will be small. If it is just a simple 400 volt slash 400 or 400 slash 200, then certainly window space factor will be 0.9, 0.8. But if you are having 11 kV, 20 kV, 33 kV something, then this window space factor, if I go back over here, this KW factor will be small. Now how you are going to decide this KW? There will be tables given to you. Those tables are based on the value of voltage that is inside your transformer. So now if I am talking about this KW, for this single phase transformer, this KW on the numerator, what I have? Actual copper area in the window. Now if I go back on my diagram, if I just zoom in over here, in this window, if I take my low voltage winding कैसे होगी? एक कंडक्टर ये होगा, एक कंडक्टर ये होगा, एक इसी तरह से होगा, एक और होगा, एक और होगा, एक और होगा, and in this way you are going to fill whole of this low voltage winding like this. I am using circular conductors because I am assuming it's a small transformer. But as we will progress in this course, I will tell you that conductors can be square or rectangular shaped as well. Okay? So this is low voltage winding conductor. Similarly, low voltage winding conductors here on this one. And similarly, there will be high voltage conductors in the high voltage winding. And certainly they will be of smaller size because their current is small. So here this is that high voltage conductor over here like this. Now I want to find out the total copper area. How I can find out? I know this is N1 by 2 number of turns here because half of the turns are on this winding, half of the turns are here. So what is the area of the low voltage conductor over here? Let me use the same green color. This is A1 और कितने नंबर ऑफ टर्न्स है यहाँ पे N1/2. यहाँ पे कितने हैं A1 multiplied by N1/2. half turns इधर थी, half turns इधर थी. So if I add these two, the total is A1 into N1. So this means that if I go back on my KW formula, KW is the actual copper area in the window. This is equal to A1 into N1 for the low voltage winding plus A2 into N2 for the high voltage winding, copper area, and divided by the window area AW. Now window area क्या है, इसकी length width क्या है, ये हम आगे जाके देखेंगे. Just for now, keep this one as the window area. Now, if you are having this A1 A2 plus A2 N2, now here we know, back to this current density formula, can I write this delta 1 equal to I1 divided by A1? Current density कैसे निकलती है? Current divided by the area, amperes per meter square. So I can write this one as A1 equal to I1 divided by delta 1. Same thing. And similarly, I can write A2 equal to I2 divided by delta 2. So I can now use these two equations in this below. Now this becomes equal to I1 N1 divided by delta 1 plus I2 N2 divided by delta 2 divided by AW. सब कुछ है, सारा कुछ है, पूरे विंडो एरिया क्या है, बल्कि इनफैक्ट सिंस आई एम टॉकिंग अबाउट दिस वन, वी विल कम एट दिस वन सम टाइम, बट दिस विंडो एरिया इज एक्चुअली बेस्ड ऑन दिस डिस्टेंस. दिस इज कॉल्ड एज द लेंथ ऑफ द विंडो, LW. ये वेरिएबल्स हैं, ये हम बाद में जब हम टैंक डिजाइन कर रहे होंगे ना, देन दिस LW विल बी डिसाइडेड, ठीक है. एंड देन दिस वन इज कॉल्ड एज द हाइट ऑफ द विंडो. सो LW into LW into HW is actually AW, the width of the window. Okay, but we are not concerned with that at present because we are just interested in some other. Now, since I just told you that delta 1 and delta 2, they both are almost going to be same. Okay, unless and until there is a big transformer and you are going towards there. So I can write KW equal to I1 N1 plus I2 N2 divided by delta AW. Now I am not writing delta 1, delta 2, I am just using delta because this is the same thing. Now I1 N1, I2 N2, what are they? Ampere turns on the primary side, ampere turns on the secondary side, and assuming it's an ideal transformer, ampere turns on the primary and ampere turns on the secondary, they both are same. So this means that I1 N1 is equal to I2 N2. They both are same. So this means that I can write my KW equal to 2 times, now I can use anyone, N1 or I1, it's totally up to me. I am going with N1 I1 divided by delta AW. This is my final form of my KW equation. Now from this equation, I can easily take out what is N1 I1. N1 I1 is equal to KW into delta AW divided by 2. Now why I have taken this N1 I1 on the other side? Because if I go back on my equation, here what I had N1 I1 here as a common term. Now in this equation, let me call this one as equation A. So if I now put this value in equation A, so what happens, this F equal to 4.44 F into phi m into, let me just go over there, this is N1 I1, N1 I1 is KW delta AW by 2 into 10 raised to power minus 3 kVA. This 2.22. So now what is S? S is equal to 2.22 F. Now I can open this phi m also. This is equal to BM into AC. AC is the core. and then I have kW delta AW into 10 raised to power minus 3 kVA. This equation is the inform. Now in this equation, kW is going to be used from a table. That factor will be given. DM based on the material. S will be required by you because you are designing a transformer. AW is the window area. If you are designing a transformer something like this, then window area are decided already. You won't find a different window area every time. So window area is also decided. Current density is what you have going to choose. So now here you can easily find out AC. So if you are designing a single phase core type, you are going to have just AC found out by this formula. So S is equal to 2.22 FBM AC kW delta into AW. Now this is single phase core type. Now if I move on further and take this to the second case, that is single phase shell type. Now what is a shell type transformer? Just like this one I have over here. Now in a shell type transformer, you have something like it's not actually very good. Actually my screen is now cracked. Okay, so this is a shell type over here. Now, up till now in the last lecture I told you that in a shell type transformer, you are going to first place the low voltage winding and then you are going to place the high voltage winding just like this. Now there is another type of winding, same in the shell type transformer, in which first of all you are going to place the low voltage winding as close as possible to the T structure. Similarly here on this side, and similarly low voltage winding here, low voltage winding here. Then afterwards the next is the high voltage winding which you are going to place here. Then high voltage winding here, high voltage winding here, and the last one again is the low voltage winding here, the low voltage winding here. Now what you have done, you have bifurcated your low voltage winding into three different parts. 1/3 is here, 1/3 is here, 1/3 is here. So what you have done, you have effectively sandwiched the two windings together, and this type of winding is called as sandwich winding over here. Now if instead of this I had just first of all the low voltage, then some insulation and then the high voltage, that type of winding was called as concentric winding because everything was concentric on one center, or you can call it radial winding. Okay. Now if I go again inside over there, a question may arise over there, how you are placing this red color winding, which is actually the high voltage winding, closer to the core. Now here if you see over here, I am not placed this red color winding closer to the upper part. I have placed it sandwich in between, and certainly this distance over here will be a little large as compared to the other winding because the insulation is large. But the advantage of sandwiching the two windings together is this, that you are going to have more flux linkage. So it's better. Now same formula applied on this single phase core type. This is the low voltage, this is the low voltage, this is the low voltage winding, this is the low voltage winding. Now in this one, window area, this is that window area. This is that window area AW. Now same formula, if I want to now write down KW. Gee, what will be KW this time? यार ये यही मसला है इसके साथ. still not very better, but I don't know, projector का मसला है. Okay, anyway, so you have this window area AW over here, and in this one you can see this is low voltage, low voltage, low voltage. So how many number of turns are there in this one? N1. What is the cross sectional area of the low voltage winding? A1. So here easily same, this is A1 N1 plus A2 N2 divided by the window area. Now I am not going to do the same calculation because the answer is the very same over there. You will arrive at the very same S. I am just going to write down the same S over there. The same S answer is 2.22 F A C D M delta KW. Sorry, this is AW also, into 10 raised to power minus 3. You can do the calculation yourself. Actually that's the same thing that we have done in the previous one. So single phase core type and single phase shell type, they both have the same design equation over here. Now if I go on towards the third one, which is very important one, which is actually the basis of our whole distribution design transformer, I am talking about three phase core type transformer. Now when I am talking about a three phase core type, and if I draw this three phase core type, this is my three phase core type transformer. Sorry about this, is not a mismatch, दोनों साइज बराबर होने चाहिए थे लेकिन है नहीं, ठीक है. So if I have now low voltage winding and high voltage winding again on this transformer, first of all again near to the core I am going to place the low voltage winding. Here again low voltage winding, here again low voltage winding, and here again a low voltage winding, here again the low voltage winding, here again the low voltage. You can write down LV, LV, LV voltage. And now this is a three phase, so there are three phases over there certainly. So there are three limbs, and then the high voltage winding, this is going to be the high voltage winding, this is going to be the high voltage winding, and space is a little cramped over here, but anyway I'm trying to, and sorry about this one. This is low voltage, and similarly again this will be. So this is a three phase core type transformer, as you can see over here. Now the interesting thing, this time window area is this. This is AW. Now this time when you are going to calculate that KW, this time it is not just going to be A1 into N1, this time it's going to be 2 times A1 N1 plus A2 N2, because there are two phases. एक इस phase का है, this one, and then you have another phase over here, this one, another phase over here, this one. So this time it's 2 times. So when you are going to calculate this KW, this is going to be 2 times divided by your window area. And now this time when you are going to have this N1 I1, I am just skipping the steps and just straight away going on towards N1 I1. This N1 I1 is equal to, this is delta KW AW divided by 4. And if I go back on the formula, that is S, now this is a three phase transformer. So this time it will be 3 V1 I1 into 10 raised to power minus 3 kVA. Okay? Because V1 I1 was phase voltages. So I have 3 V1 I1. Now here, over here, instead of V1, I will write 3 into 4.44 F into DM into AC into N1 I1 into 10 raised to power minus 3, and here this is kVA. Now here in this one N1 I1, I can replace this one by this. So when I will get over here, this will be S equal to 3 into 4.44 into F into BM AC into, now this is delta kW AW by 4 into 10 raised to power minus 3 into, oh sorry, actually this is kV. Now this 4 and this one, this is 1.11, so the final answer is 3.33 F DEM AC delta kW AW into 10 raised to power minus 3 kV. So what you are having, this time the factor is different. Variables are the same. If you see, in the previous one it was 2.22. This time this is 3.33. So if you, this, what is telling you? This is telling you that if you are having a 3-phase transformer, you can actually get more kV output from your same area of the window, same current density and same something. You are getting 1.11 times, actually 1 point something times more than the single phase transformer. And if you repeat this very same for a 3-phase shell type. Now for shell type, as we did in the last lecture also, on the shell type your core is going to be something like this. So this is my window here, this is my third window, and over here. So again, what will be the low voltage winding? Now here it's totally up to you. You want to go with the sandwich winding like this, you want to go with this like this over here, just like I did in the single phase, or you want to go with the डिस्प्ले फिर खराब हो गया, बड़ा मसला है। यार जरा ये जो स्थान वाली लैब है ना, मैंने कह चुका हूँ इनको, इन्हें भी कुछ नहीं कहना। चेयरमैन, मैंने इनको पिछले हफ्ते भी कहा हुआ था कि ये इसको ठीक करवाएं, अभी तक उन्होंने ठीक नहीं करवाई, तो एक दफ़ा चेयरमैन साहब तक बात पहुंचा दें ताकि अगले हफ्ते तक कम से कम ये ठीक हो जाए, ठीक है? अदरवाइज ये कभी नहीं ठीक करेंगे, इसको ऐसे ही रहने देंगे। एंड आई नीड दैट HDMI so that the quality is better. Okay, so I have this one. So again, if I zoom in over here, this is the the low voltage winding, the low voltage winding, low voltage winding, low voltage, low voltage, low voltage, and here this is the high voltage winding, high voltage winding, this is the high voltage winding. Now what is window area over here? Window area is this one. Okay, now when I will have this window area, you can replicate it for the other windows yourself. So when I have this one kW factor for a shell type, this kW comes out to be 2 times I1 N1. I'm straight away writing down the answer, you can do it yourself, divided by 8. Okay? Because window area is including this one and this one, because the first phase window area, please remember, this is very important, window area is both of these. ठीक है, इस केस में दोनों हैं, क्योंकि एक फेस बनता ही इन दोनों से है। प्रीवियस केस के अंदर व्हेन वी आर हैविंग दिस वन, विंडो एरिया इससे और इससे नहीं बनता था। क्यों? क्योंकि इस एक के अंदर वन फेज पूरा हो जाता है। ठीक है, विंडो एरिया इज दैट एरिया इन विच वन फेज ऑफ द वाइंडिंग्स आर कंप्लीटली डन। ठीक है, तो इसके अंदर पूरा हो जाता है, तो यहाँ पे आपके पास विंडो एरिया सिर्फ ये है फेडेड पोर्शन। इन शेल टाइप इट इज बोथ ऑफ देम। KW. So here this time you have KW equal to this form, and your S comes out to be, let me drop this one. So your S, S comes out to be, I am writing down the final form, this is 6.66 FACDM delta KW AW into 10 raised to power minus 3 kVA. This is your final. Now, one question. This factor is 6.66 in three-phase shell. This factor is 3.33 in three-phase core. क्या advantage है? In shell type, you can get better output kVA from the same side. But if you see in a shell type, the windings are jam-packed. There is no cooling mechanism involved over there. So, three-phase shell type transformers are better suited, which are going to run for only 5 or 6 hours. A power transformer that are connected with grid, maybe a power plant, Tarbela, Mangla, or any other power plant over there. But in a three-phase core type, something like this over here, they have an ample amount of cooling. So they can run for 24 hours a day, 365 days a year very easily without any disruption. Okay? So three-phase core type, they are mostly used for the distribution, and if you have the three-phase shell type, they are normally used for the power transformer. Now, one thing very important, I will share this doc file with you also from where I have done this. These are also available from R.K. Agarwal. One thing in this doc file or in any of the books which we are considering, this S over here, we know it is apparent power. Now, in your book or in these notes which I have at present, they have used the variable Q over there. Now, don't confuse this Q with the reactive power, because whenever a transformer is designed, we are not concerned with the reactive power. We are only concerned with S, the apparent power. So instead of S, they have also used Q sometimes. So don't confuse it yourself. Okay? So what I am practically asking you, this is actually the same file. Let me go on towards that one. This is the same notes over here which I have compiled. This is the same. You can see the same core type transformer over here. The same single phase shell type transformer, sandwich winding. This is the same three-phase core type window over here. Okay? And then this is the same area window having this one over here, and this is the same three-phase shell type, the same formula 6.66 over there, and you can see they have written Q, okay, because Q and S, they are interchangeably used, but I will try to use S over here in the class. Next thing, before I just make this on off over here, choice of magnetic loading. If you see over here, I have 3 different types of material. First one is called as normal silicon steel. Second one is called as hot rolled grain oriented silicon steel. The third material is CRGO. Now CRGO is the best material, in which whenever those silicon steel sheets were prepared, they were rolled, and in that cold state, silicon was rolled on that silicon steel stuff over there, so that they can have a magnetic field density of 1.4 to 1.7 Tesla. Now if you are going for a hot rolled grain oriented, which is a little less, you can see the magnetic field density is 1.2 to 1.4 Tesla. And if you are having something, a simple silicon steel just like this one, then you can only have 1.1 Tesla. Now higher the value of B means you are going to use less size of your machine or your transformer. Now in this note you are seeing 1.7 Tesla as the maximum. Tesla, I am talking about the Tesla company, which is having an induction motor car. Their motor size is almost the size of maybe like this bat. I am talking about the width and diameter, maybe the height wise is a little bit more. Their size or the horsepower which they can achieve from that machine is more than 100 or 150 horsepower. It's huge. Reason, they are using better materials which can have the saturation of the knee point at approximately 2.4 Tesla even. Now since in the last 15-20 years the motors category or the materials have not changed that much, because there was no investment in this one. Now since electric cars are going to be the next future, You will see a little bit more advancement in materials. You will see ceramic materials more being used over there because they can have more better magnetic field strength or saturation. So you will see this value of Tesla reaching to new heights. But sadly in Pakistan, even the transformers which you get from Hall Road, they are not even using silicon steel. कोई वैसे मसला नहीं है कि हो सकता है इसमें भी सिलिकॉन स्टील ना यूज की हो. मे बी दे आर यूजिंग जस्ट, अक्सर वो लुक के डब्बे होते हैं उनको काट के दे आर यूजिंग दोज एज लेमिनेशन शीट्स. एंड व्हेन यू आर यूजिंग इवन दोज एज लेमिनेशन शीट्स यू हैव टू पुट अ रेसिन इन बिटवीन ईच लेमिनेशन. मैं शायद इस ट्रांसफार्मर को आपके सामने खोलूं तो आपको इसमें से रेसिन मिलेगा भी नहीं. क्यों? क्योंकि वो लगाते नहीं, या अगर लगाते भी हैं तो वो इतना सब स्टैंडर्ड है कि हीट अप होने के बाद एक इवेपोरेट. सो सिलिकॉन रेसिन अगर आपने नहीं लगाया, देयर इज नो एडवांटेज ऑफ द लेमिनेशन, क्योंकि फायदा ही लेमिनेशन का तब है व्हेन यू कैन कन्फाइन द फ्लक्स इन ईच लेमिनेशन सेपरेटली. अगर लेमिनेशन से फ्लक्स उधर जा सकता है, दिस मींस एडी करंट्स कैन ट्रेवल और एडी करंट लॉसेस आर ह्यूज. इसका मतलब ये कि आप लेमिनेशन ना यूज करते, एक सॉलिड लोहे का ब्लॉक यूज कर लेते, दैट वुड बी इनफ. ठीक है. सो दीज आर थ्री डिफरेंट मटेरियल्स ओवर हियर. Normally Pakistani industry, when I'm talking about some good manufacturers of distribution, they use cold roll grain oriented steel. And I also missed in the last lecture also that transformer is the highest efficient device in electrical engineering. आपको इससे ज़्यादा efficient device कोई नहीं मिलेगी. No MOSFET, no GAN device, no transistor, nothing. 99.99% efficiency has been achieved. So it's the most efficient device and you can control it by controlling the core losses, by controlling the I square R losses, using better materials, better cooling purposes over there, so you can have a higher efficiency of your transformer. In Pakistan still, मैं भी कहता कि 99 है, it is still 98 or 97 something efficiency for power transformer. For distribution transformers it may be a little lower side because they are working for 24 hours a day and they have some losses over there, but they are still in the bracket of 90% plus. Okay? So material very much important in electric machine design. Either you are using CRGO steel, HRGO steel or normal silicon steel over there. Okay? This is up to now. We will talk about this electrical loading and other stuff in the next lecture. Any questions, Ji? ये वेबसाइट पे होंगे. And I have made your everything. Whatever I am doing over here, this is available on the YouTube channel, or you can have the links over there. You can see. कौन सा ये वाला? अच्छा ये मैं देख लूँ, ये मैं कर लूँ. The links for the lecture, the YouTube channel, section A and section B, and one thing very important. Since I am repeating the same lecture again and again, just after section B, I did it for section A over here. So maybe शायद कोई एक दो points मेरे से miss हो जाए, because I have this mask on, I am also perspiring, so humanly I can miss. So just have a habit of when you are reading your or having those lectures again, go with the section B lecture. ठीक है, चीज वही है, लेकिन हो सकता है कोई एक दो चीजें मैं मिस कर जाऊं आपको पढ़ाते हुए. ठीक है. So if you are revising it, just go through the section B YouTube lecture. That is going to be a little bit more. And by chance, section B का lecture 9:25 से start हो रहा है and it's ending at 10:50. आप लोगों के पास 10:50 से लेके I guess 12:05 तक का टाइम है, something like that. It's smaller. ठीक है. तो मुझे थोड़ा सा speed wise भी तेज रखना पड़ेगा and I have to confine it. ठीक है. So if you are revising it, that's why I am recording both of these lectures and they are available on the YouTube channel every time. ठीक है. Any questions, जी? No questions? Welcome. यार ये ठीक करवा लेना प्लीज प्रोजेक्टर, इसके बगैर थोड़ा मुश्किल है हमारे लिए. 38 only. 27 120 131 46. मास्क नहीं पहना हुआ. ये चेयरमैन साहब ने स्ट्रिक्टली कहा है जो मास्क नहीं पहनेगा उसको अटेंडेंस नहीं लगानी. 31 122, 34, 33, 179, 123, 105, 107, 112, 110, sorry, 108, 52, only 9, 103, 43,
42,
42, 106, 132, 146, 148, 128, 143, 2, 41, only 41, 140, 135, 136, 142, 113. So